So hello everyone and welcome to week number 13. This is class number, I don't even know. I mean, if we haven't missed any classes, this is our 25th class. I don't remember if we're missing anything. But this is certainly week number 13. And we are going to continue with regression and analysis and correlation. So chapter 17 is titled More on Correlation and Regression. That means we've already had some, and here's some more. More on correlation and regression. Then I had mentioned this last, oh, someone already texted something. What did they say? Did he grade exam 2? It's a good question. Did he grade exam 2? This past weekend, I graded a lot of my high school work, so I did not yet finish exam 2. I have more grades than I have up on Canvas, but I have not finished everyone's grades yet. So hopefully that will be done, hopefully this week. My chemistry, I'm taking a chemistry class. I'm sure I've mentioned that before. And my teacher takes, she says she needs 3 weeks to grade an exam. So I kind of feel that I'm not horrible for taking 2. But anywho, so we're back, we're on correlation and regression, and let's just recap what correlation and regression is, what we've done so far. Correlation is, when you believe that two quantitative variables have some sort of connection between them, where one will have some influence in some way on the other, or perhaps not even influence. Perhaps it's just, as the word suggests, correlation, that there's a connection between them. Maybe behind the scenes something is going on that we don't really see. But correlation is asking whether or not there's a connection. And then regression is actually finding that connection, right? Regression is when you actually go ahead and you actually calculate the best fit line, okay? And what we did last chapter is we kind of talked about it qualitatively, but we didn't actually figure out a way to actually compute it. And that's what we're going to do this chapter. We're going to actually come up, it says, towards a formula for the correlation. So let's look at this example here. It says, this scatter plot shows the 37 students on the first and second tests of a semester. The axes have been located at the mean test score for test 1 and the mean score for test 2. So we're accustomed, when we create our axes, to have 0, 0 where the lines meet, right? That is what is normally done. They didn't do that here, okay? They took the average for test 1. Test 1's on the x-axis, so they calculated the average behind the scenes because we don't have the exact scores. But they calculated the average to be 73.6. And they did the same thing for test 2. They calculated the average to be 70.5. And the center of their axes is where those two meet, okay? So here's the scatter plot. And the question is the association linear? And it says that is, do the points form an elliptical cloud, right? Do we have like an ellipse where the points are kind of inside of that ellipse or not? And the answer is, what would you say? Yes, so it certainly looks that way. I wouldn't call it strong correlation, at least not on this scale, but yes, we certainly have this correlation. What is the direction of the association? Is it positive, negative? Okay, we got a plus sign, so it is positive. It's going up from left to right. And then it says, what percent of students had their above average scores on both tests or a below average score on both tests? So look at the dots and answer that question. What percentage had their above average scores on both tests or their beneath average scores on both tests? What would you say based upon that scatter plot?
Well, it doesn't look like it's completely 50-50.
Well, remember, it's not asking for one or the other. It's saying in total, what percent of the students had scores either above on both or beneath on both?
So would that be like the top right corner is above on both?
Like 60?
Yeah. right? The top right corner. So all of these guys here are above on both.
Oh, I see.
And all of these guys here are below on both, right?
Mm-hmm.
So it certainly seems that a significant majority, I would say 80%, 85%, right? I mean, who are the only ones who don't? These few ones over here, right?
Oh, okay.
Right, these are the only ones who kind of scored better on the first exam and worse on the second exam, correct?
Okay, yeah.
Right? So the vast majority of them scored either better on both or worse on both, which kind of makes sense if you think about it. That's, you know, most students are either good students or poor students, you know, or not hardworking students, you know, whatever the case may be. So, you know, these ones here, it's kind of weird because they scored better on test one, they scored worse on test two. So their performances went down. And what do you normally expect? You kind of expect that if you score well in the first, that you'll continue studying and you'll score well in the second, right? This one I can understand because this one scored worse in the first. So what did this one probably do after that? Practically, right? What did that one do? It scored bad in the first test, below average in the first test, right? So
Basically what they did, either study, like you mean?
yeah, they hunkered down and they studied, right? So, you know, they said, okay, well, this isn't working, whatever I'm doing. Let me
Gotta bump up the average
yeah,
somehow.
let me bump that up, right? Let me do what I can. These ones I get, these ones I get, these ones I get, these ones are just bad. Like, come on, don't go down, you know, go up. Okay, maybe it was an anomaly. You know, people have, I mean, the truth of the matter is I was taking, you know, physics years ago and I was doing so well in the class that I stopped going to class. I'm like, I don't got to go to class anymore. I'm so far ahead of everyone else, I'm going to get an A. And sure enough, I did get an A. But like the last 3 weeks of the semester, on the final, I showed up, I see these, I'm like, I have no idea how to answer these. Because I didn't go to class. So I got a bad grade in the final, even though it was still high enough to get an A. So sometimes, you know, that happens. You know, you're doing so well that you're like, oh, I don't need to do anything. And then, you know, you score worse. But anyways, the point is that the majority of them are either here or here. And that's going to matter. If the association in a scatter plot is positive, then points with X values that are above average tend to have Y values that are above average. And when they have X values that are below average, they tend to have Y values that are below average, right? If it's linear, we expect a plot that goes like this, which means we expect lots of over here and lots over here and not so many there and there. So either both X and Y above or both X and Y below, but not really one above and one below. Okay, otherwise, if it was more that way, it would be a negative correlation. Okay.
Professor, you said it was above and then below?
No, above, or both below, right? We expect stuff to be here along this line, right? And this line is above, and below. We don't.
I think he's talking about the for the sentence that's the if the association of the scatter plot is positive.
Oh yes, then
Yeah.
either then it's
So it was above and then below.
Yeah, so above. Yeah, so this is above and that one's below. That's what you meant. I'm sorry.
Okay, cool. Thank you.
You are welcome. So draw horizontal and vertical lines at the approximate locations of X bar and Y bar on each of these scatter plots. All right. Well, I mean, if you kind of ignore the two-dimensional pattern, if you drop every point down, so you just kind of look at them along the x-axis, which is kind of hard to do. The average looks to be somewhat in the middle, to be honest, right? It's just right, and the y average tends to be maybe a little lower. It looks like there's more of them at the bottom than there are on the top. So maybe I would do something like, I don't know, like this. Would that seem reasonable for this being the average of the x's and the average of the y's? I'm not a very visual person, to be honest myself. You know, some of you have mentioned in the past, you know, when I teach in certain ways that you're visual learners. I'm not a visual learner myself. I'm not very good at that, but does that seem relatively reasonable?
Sure.
Yeah.
I mean, is it so out of whack that you're like, no, that can't be true? I don't think that is
No, I mean, like the data is just spread out. It's very spread
right.
out and
It's
not
tough to see. It's
wrong.
100% tough to see. But you know, if we had the best fit line, remember the best fit line does have to go through the center. So does that seem like it's a relatively okay best fit line?
Yeah.
Your own actually hits a point or two. So
Yeah, but that doesn't mean anything itself. The hitting the points is coincidental. That seems relatively okay. And therefore something like, it looks like the X's are some, yeah, it looks like actually, I don't really see any, whoops, that was not good. I don't really see any predominance one way or the other here. I don't know, something like that. Does that seem okay? I don't know. I'm horrible about this. But let's see where we're going with this. True or false? The stronger the positive association, the stronger the tendencies for the XY pairs to either be both above or both below. Would you agree with that? Would you agree with that sentence?
I mean, like in terms, is it like comparing it to the second graph? Because if so,
Well, the
I
second
would
one,
want to say yes.
yeah, the second one seems a lot stronger, correct?
Yeah, that's the stronger one. So I would want to say yes because it does show more in the bottom and the more in the upper portion. Like you said, I forgot what quadrants they're called and everything, but
The top right is the first quadrant, and then
Mhm.
it goes counterclockwise.
clockwise. Got it.
Counterclockwise.
Counterclockwise.
Counterclockwise. So first, second, third, fourth. So yeah, this one, all of the data points are either in the first quadrant or in the third quadrant, right?
Mm-hmm.
Which is very strong positive, as we saw in the last one. This one has some in the first, some here, but then it's got these stragglers. And in fact, there's like more.
Mm-hmm.
And
it's not
right?
the stronger association.
Yeah, exactly. So this is a true statement, right? The stronger it is, the higher the likelihood that we're going to have lots of them along that line.
Mhm.
If the association is negative, which is exactly the opposite, then point with X values that are above average. So if the X values are to the right, then the Y values are going to be below average, right? Right and down. And point with X values that are below average, X values to the left, we're going to have Y values that are where? Above average, right? We're going to have a line that goes in the other direction. That seems reasonable, correct?
Yeah.
Okay, hopefully. So finally here, without any proof or explanation, finally here is the formula for the correlation formula, for correlation.
That's a big formula.
It's a big formula. It's a big formula, 100%. Okay. So where does this formula come from? Well, they're not giving it to us. They're just giving us the formula and say, plug things in, pop out a number, and you're done. They're not explaining where it comes from, but let's make sure we understand what everything is. X bar is the X average.
Mm-hmm.
Y bar is the Y average. S sub X is the X standard deviation. S sub Y is the Y standard deviation. N is the number of data points. So far, so good, right? These are not, these so far nothing is like, wow, where'd that coming from? Everything makes sense. We've seen this before, I believe. This means you're going to add up. So you're going to calculate this thing for each XY pair and then add them all together. You do it for the first pair, the second pair, the third pair, all the way to the nth pair if we have n of them. And then you are going to add them all together and then divide by n minus 1. That is the formula for the correlation. At the end of the day, calculators can do it. Your computer can do it. It's really tough and annoying to do it by hand, although it can be done. But in general, that's not how we do it, right? Because it's annoying. What is the name for this, by the way? X minus X bar over SX and Y minus Y bar over SY. Remember what those names are, what they're called? We've seen those things before. What are they called?
Yeah, I can't remember.
I'm really trying to think about it. Like
data point minus average below divided by standard deviation.
mad?
What? No, not mad. Mad was data point minus average absolute value to all added together.
Okay.
Divided by,
It's the number, it's standard deviation.
well, the bottom is SX is standard deviation. It's the Z-scores.
Yeah,
Oh, okay.
Yeah. Did you even say yes, right? But you didn't say it. That's the point, right? The z-scores. Okay, so for each situation, tell whether the quantity is positive or negative. If x is above average, then what is this guy going to be? A positive or a negative value?
Positive.
Positive, right? If x is above average and the x is bigger than x bar,
Mm-hmm.
the numerator is positive. The denominator is always positive because it's a square root of a number, right? So we know that's going to work without a problem. Okay. How about the rest of them? If x is below average, what do we think for that one?
Negative.
Negative. And what about if y is above average?
Positive.
Positive.
Positive. And what if y is below average?
Negative.
Negative. Okay. Now look what we're doing in this thing. We're multiplying those two together, correct? Yeah. Sorry, you have a question?
Yeah, was if x is above average, then the z-score thing, that one's positive?
If x is above average, then the z-score is positive, right? As expected.
Yeah, okay, got it, thanks.
Okay. And if x is below average, then what do we expect to happen? It's going to be negative, right? And same thing with y, above average and below average, etc. Right? These are not shocks, correct? Okay. Now look at the formula for correlation. What do you notice about that formula for correlation? We are multiplying z-scores before adding them, correct?
It looks hella complicated. That's what I noticed.
100%. 100% it looks complicated. I'm not arguing with you on that. But what are we doing? Let's break it down. We're taking this z-score in the x direction and this z-score in the y direction, and we are multiplying them together, are we not?
Yes.
Yes.
If they're both individually positive or they're both individually negative, then when you multiply them, what do you get? A positive or a negative?
Positive number. If they're both positive, you get positive. If they're both negative, you still get positive.
That's correct, which means if we have positive correlation like this, and then we have lots of them here and lots of them here,
Mm-hmm.
we're going to have lots of positive numbers in that sum.
Okay.
Does that make sense?
Mm-hmm.
And if we have lots of positive numbers in that sum, then you can understand why the correlation would end up being a positive number, right?
Yeah.
What if it's the other way? What if it's like this?
Opposite.
So a lot of negative numbers.
Then there's going to be a lot of negative numbers in the sum, and the correlation is going to be negative, correct?
Mm-hmm.
So that is, well, so that's what we're doing over here on this slide. When both x and y are above average, the product is going to be what?
Positive.
Positive. When they're both below average, the product is going to be?
Negative.
Oh, well, when they're both below average,
positive.
positive again.
Mm-hmm.
Negative
Because
times
they're
negative is
both
still positive,
negative
right?
times negative is a positive.
Okay.
Right? Remember, when they're both above average or both below average, in both cases, right, when we're like this, and you have lots of them here and lots of them here, and when I multiply and add, I expect to get a positive number, correct?
Mm-hmm.
Yes.
Okay. So for a positive association, most of the terms will be positive. So R should be
Positive.
positive, right? So R should be positive.
So then when do we get a negative?
Well, if it's a negative correlation, then instead it's going to look more like this, right?
Mm-hmm.
And you're going to have lots of them down here,
Okay.
and you're going to have lots of them up here, correct?
Yeah.
Well, down here, X is positive and Y is negative. So it's going to be a negative number.
Mm-hmm.
And up here, X is negative, Y is positive. So it's going to be a negative number. And in
Mhm.
that case, right, you agree?
Yeah.
And in that case, when you add them all together, you are more likely to get a big negative number out of it,
Oh,
which is why in this case, the correlation is going to end up being a negative number. Does that seem reasonable?
I think so, but would it be possible to do an example?
Well, we're coming to an example right now. First, I want to kind of give the theory.
Mm-hmm.
Then once the theory is done, then we do an example. Okay. So first, let's just fill this out. So when X is above average and Y is below average, which quadrant are we going to be in when X is above average and Y is below average? Which quadrant is that?
Second?
X is above average
Oh, wait a minute.
and Y is below average, correct? When X is above average and Y is below average,
4?
That means you're on the right side if it's X is above average, and then below average would move down. So the fourth quadrant.
we would expect to be in the fourth quadrant, correct?
Mm-hmm.
Okay. So is the product in that case going to be positive or is the product going to be negative?
Negative.
Negative.
It's going to be negative because we have a positive number times a negative number, right?
Yes.
Now, when X is below average and Y is above average, which quadrant are we going to be in now?
When X is
When X is
below
below
average.
average and Y is above average, which quadrant are we going to be in now?
Second?
We're going to be in the
2.
second quadrant, right?
Yeah.
Right? We're going to be up here because
Yeah.
X is below average, so we're to the left, and Y is above average, so we're up, correct?
Mm-hmm.
In that case, do we expect it to be a positive number or a negative number?
A negative.
Negative again. So for a negative association, most of the terms will be negative. So R should be
Negative.
negative. Positive correlation, lots of positives and positives. And when you add them together, you're going to get a big positive number, not a big positive number, but you're going to get a positive number. For negative correlation, we got lots of negatives and negatives, negatives down here, and negatives up here. So when you add them together, you expect to get an overall negative number. Now, if the association is weak association, then we expect essentially just as many positive terms as negative terms because you have some here, and you have some here, and you have some here, and you have some here, right? You have some all over the place.
Yeah. So the weak is just like everywhere and not like defined as negative or positive or strong.
Yeah, I mean, with weak, you can, with weak, you can still talk about weak positive and weak negative, but
Mhm.
essentially weak is like almost non-existent. It's like, I don't
Where there's like no correlation.
Yeah, it's like the
Yeah.
correlation is so minor that it's almost like you don't even see it happening at all.
Okay.
In that case, you're gonna have lots of them over here, and lots of them over here, and lots of them here, and dinner time, and lots of them here. So when that happens, you expect it to add to somewhere in the vicinity of 0 because most things cancel out.
Hmm.
Does that make sense?
Yes.
Pilar, does that make sense at all?
A little more, yeah.
Okay, good. We'll do an example in a second. Okay.
What was the blank one for?
Sorry, one more time. What was the question?
The fill in the blank. What was it?
Last one.
Fill in the
For a
blank.
week, close to the
page
weak association R would be close to 0, right?
For the weak association, R will be close to 0. That's correct.
Okay, thank you.
For the weak association, R will be close to 0. Okay. So the question that you, of course, want to ask at the same time is, what exactly does R represent? Like, I know it represents the correlation. I get that it represents the correlation, but what does it mean that R is positive, negative, this, that? What do these R values actually represent?
Whether how like strong.
Yes, it does represent how strong, but we want to go a little deeper than that.
Okay.
Okay, not just how strong, but one deeper level. So for that, it's actually not R that we're going to be looking at, the correlation. It's actually going to be R squared. We're going to take the R value that we got, and we're going to square it. Okay, and here is an understanding of what R squared represents, because it's not straightforward. Let me see the following question. Look at this scatter plot. Okay, this is just a generic scatter plot. Are all the Y values for all the dots exactly the same?
No.
No, I mean, look at them. There's like what, 8, 7, 8, 9 dots there. Are they all the Y values the same? No, there's one up here. There's a couple here. There's a couple down here. And there's more over here. All the Y values are different, right? Can you give me 2 reasons why the Y values are not all the same?
So for like grade, course grade, these are like averages for course grade.
Yeah, but don't worry about the details of the problem.
Okay.
Just in any scatter plot that you ever have, give me a reason why the y values will not all be the same.
Because you have different data points.
Okay, well, they are different data points. So the question is, why are the y values for all the data points not the same? Give me a reason why all the y values are not all going to be the same.
Because you're
The X is there's a different X for each
Okay.
Y.
So the most logical answer is they have different x values,
Okay.
right? Why would they have the same y for different x values? Right? In this case, in this particular example, as the number of absences in class change, the grade is going to change. That makes complete sense. People who are absent more are probably going to score worse. It makes perfect sense. But you'll notice there's 3 people with 0 absences, and yet they still have different grades.
Right.
Mhm.
So that can't be the only reason why y values are different.
Studying and depending on if they do homework and if they do well on tests.
Hmm.
So there are other considerations besides absences at play. And this particular graph is not considering those,
Mm.
right? So there's other things that might play. It's not just how much homework they do or how much they, it could be just their prerequisite classes, what they've already taken. People are just smarter than others. There could be genetic, there could be many things that we're not considering, right?
Mhm.
So there's 2 reasons why the y values are different. 1, different x values. 2, there could be other things that we're not considering.
Okay.
The question is, what percent of the reason why the y values are not all the same is due to the absences in our case, to the x values? How much is due to the changing x values and how much is due to things that we're not considering? Right? Y values are different for 2 reasons. How much is due to the first reason and how much is due to the second reason? The answer is r squared.
Got it.
R squared tells you what percent is due to the x values changing. If I get an r squared value of 0.5, that means 50% of the reason why the y values are not all the same is because the x values are not the same.
Mhm.
And the other 50% is because of things that we're not considering. That is physically what the r squared value tells you. Okay? So let's look at this example here. We have grades dependent upon absences. And as expected, as the absences goes up, the grade goes down, right? That's not a shock. The R value is negative 0.8. When I square negative 0.8, what do I get?
1.6.
I didn't say multiply it by 2. I said
Oh,
square.
oops.
Oops.
6.4.
How much?
6.4.
Wow. Okay. So that's 0 for 2. Come on. Don't strike out on me.
Oh my God.
Don't strike out on me.
0.64.
0.64.
Okay.
So we say 64% of the reason why the grades are different is because of absences. And the other 36% is because of things that we're not considering, like how hard they work outside of class and how smart they are in the prerequisite classes, and how much sleep they get, and this and that, and all the other considerations. We can only attribute 64% to absence. Go ahead.
Can we talk about how we did that again?
Yeah, how did we get to so I'm thinking we have to solve for r first and then
Yeah.
square it
You first solve for r or have your calculator
using
do
the
it for you.
gradient formula.
Yeah, either the above formula, which is a lot of work, and I really hope, oh, okay, we'll do one. Talar wanted us to do one, we'll do one. But you calculate the r value, either using the formula or having your calculator do it for you, and then you square it.
Okay.
Okay. In our case, we got 0.64.
Well, doesn't it say r equals?
Yeah, they did it for us. They got r equals negative 0.8.
So then
That's the
So then
correlation.
r squared is 0.64.
So r squared is negative 0.8 squared, which is 0.64.
oh, okay. So
Okay.
60%, okay.
0.8 times 0.8 is 0.64. So the negatives make a positive. So the question is, how much of the reason for the variation in grades comes from the variation in absences? And the answer, 64%. When I look at this data, I say 64% of the reason why grades differ is because absences differ. And 36% of the reason why grades differ is due to other things. That is the physical interpretation of R squared. Okay, so if I was trying to come up with a reason why grades suffer, would it be safe to say it's because of absences? Would that be safe to say that it's because of absences? Yes, no, maybe so.
I feel like I would want to say yes, just because it's over 50%.
Okay. So
Majority,
yeah.
not majority, but like definitely if it's over halfway, then the reason why the class is not doing so great is because a lot of them have been absent.
Certainly seems very reasonable. And in fact, would you even go one step further and say that the closer that R squared is to 1, the more that it's going to fall in an exact straight line? Because remember, if R squared equals 1, we're saying 100% of the reason is due to this factor.
Mhm.
If that's the only factor, it should be a complete and utter predictor. And therefore, it should fall perfectly on the line with no variation at all. So the stronger the correlation, the closer the R squared value is to 1, and the stronger it's going to be. Does that make sense? Yes, no, maybe so?
For now.
For now. Okay. So let's actually do this particular example. The X values are absences. We have 0, 0, 0, 1, 1, 2, 4, 7, 12. 0, 0, 0, 1, 1, 2, 4, 7, 12. Okay, they're listed again here. The course grade, 90, 98, 85, 55, 88, 75, 78, 58, 42. Those are listed here. So we have all the X values and all the Y values. If we go back all the way to the formula, the first thing we must calculate is X bar, Y bar, SX, and SY. That's doable even before correlation. We did that long ago. Okay. How do I calculate X bar when I look at all the X values?
Add them up, divide them by the number of X value.
That's exactly it. Add them up and divide by how many we have. So let's do that quickly. 0, 0, 0 plus 1, 2, 4, 8, 15, 27. 27 divided by 9 is 3. So X bar is equal to 3. I'll put it right here. X bar is equal to 3. If you were impressed, Solaire, can you write it on your whiteboard? Solaire, can you write it on your whiteboard? Come on, do my job for me.
Okay.
Okay. So add all these up and divide by how many? 0 plus 0 plus 0 plus 1 plus 1 plus 1 plus 2. Sorry, 1 plus 1 plus 2 plus 4 plus 7 plus 12. X bar is equal to 3. Okay. Now we also got to calculate Y bar. How do I calculate Y bar?
Isn't it the same thing? I did it already and I got 74.
You got 74. So I'm going to trust you. Of course, I'll know in a second if you're wrong, but yes, you were correct. Y bar is equal to 74. Excellent. Okay, so we have X bar and we have Y bar. Next, we're going to calculate the deviation of Y from the mean. So the Y value is 90. The mean is 74. So what's 90 minus 74? 16. 97 minus 74? 23. 83 minus 74? 9. Negative 19. 14. 1. 78 minus 74?
4?
4, sorry.
Okay, I know it's a tough question, I know. And then negative 16, negative 32. And then we square them.
So 4 squared is 16?
No. 16 squared is 256.
Oh, no, I'm talking about the blank one.
Oh, yes. So 4 squared will be 16. Okay. And then what we're going to do is we're going to calculate what's called the TSS, the total sum of squares. By totaling, adding up together the squares of these guys. So we're going to add up this column right here.
Oh, boy.
Oh, boy, indeed. So we have 256. Whoops. We have 256 plus 529 plus 81 plus 361 plus 196 plus 1 plus 16 plus 256 plus 1024. That gives us 27 20. The total sum of squares, at least in the y direction, is 27, 20. Now, the predicted value of y hats. So if I go back here, here's my formula. They've already done the math for us to get the formula, because the formula for the best squares regression line we didn't do last chapter, right? We never actually learned the formula for it, so we're not going to. We're just going to use it. It's 84.8 minus 3.6x. 84.8. So you want to write that down? 84.8. Don't eat. Let me eat. So y equals. Crap, I forgot already. Was it 84.8?
Yeah.
Minus what?
3.6x.
3.6x. Okay. Okay. So the question is now, why is this the predicted value, y hat? What does that mean, the predicted value? That means it's what the line tells you you would get for that x value. Not what you actually got for that x value, what the line tells you you should get for that x value. So for an x value of 0, what does the line tell you that you should get? Plug in 0, what do you get out of that?
84.8.
84.8. And we have 3 zeros, so they're all 84.8. And when you plug in 1, the line tells you that you should get 81.2. And when you plug in 2, this. How about when you plug in 4? What does the line tell you that you should get?
3.6 times 4, which is 14.4, which is 70.4.
Yeah, that's what I get, 70.4, but that's not what they have in the next line. So I think there might be a mistake here.
Ooh.
When x is 7, 84.8 minus 3.6 times 7 is not 70.4. That's 59.6, which means this is not 59.6. It's 84.8 minus 3.6 times 12, which is 41.6. So that was kind of strange.
Professor, some people are a little confused in the chat.
Yeah, sorry. What's the question?
They're asking, where did 3.6 come from?
That was given. That was right here, 3.6.
That was the equation for the best fit line.
Right, that's the actual equation.
Mm-hmm. And then for the rest of it, what
Yep.
he's doing is if he goes down to the x values, which is on the absences, that's where he said 4 and 7, you plug 4 into the x, and then it would be 3.6 times 4. Then you subtract that from 84.8, I believe that number is, and that's how you get the following numbers he's gotten. I don't know if that helps people, but
Yeah, I mean, that's exactly it. But yeah, if you guys don't understand, please say it verbally. Like, I don't always see the chat, especially when I'm in the middle of doing something. And I don't mind if you interrupt. That's totally fine. Yeah, this is the formula. Y equals 84.8 minus 3.6x, because grades are y and absences are x. So this is my formula that they're giving me. They're giving me that formula. That's not, you can't say, hey, where did it come from? Because they did the math for us. And we're not learning that. We're not worrying about that. What we're doing just right now is plugging things in.
yeah, he was doing the empty, like the whole empty column. That's why he started off with 4. So they did 3.6 times 4 and then subtracted it from 84.8 to get 70.4.
Exactly. And then I corrected these two mistakes, because when x is 7, when you plug in 7 into here, you don't get 70.4, you get 59.6. And when x is 12, you get 41.6. Now, what are the residuals? The residuals, we learned this last time. The residuals are actual minus predicted. Actual minus predicted. So my actual y value is 90.
Mm-hmm.
my predicted y value is 84.8. What's 90 minus 84.8? 5.2. 97 minus 84.8. Now I got to check the math because once they make one mistake, they can make more. 12.2. 83 minus 84.8, negative 1.8. 55 minus 81.2, negative 26.2. 88 minus 81.2, 6.8. 75 minus this, negative 2.6. Let's do this ourselves. 78 minus 70.4 is how much?
7.6.
7.6.
Oh, yeah, they're right now.
So they're right now, yeah, 58. This is negative 1.6, and 42 minus that is 0.4. And then they squared them. Just like we squared the deviations. Now we're squaring the residuals. So we got to fill in the 7.6 squared, which gives us
Squared is 57.76.
57.76. And now we're calculating the SSR, the sum of the squared residuals.
Ooh.
So 27 plus 148.8 plus 3.2 plus 686.4 plus 38.6 plus 6.8 plus 57.76 plus 2.6 plus 0.2 gives me 971.36. So we just calculated the TSS, the total sum of squares, and we also calculated the sum of the squared residuals, and we got 971.36. Everyone with me so far? Hopefully. So let's see where we're going with this. Okay. So what exactly is the total sum of squares that we're calculating it? So the total sum of the squares is part of the calculation of the standard deviation of the grades. So what TSS measures is the variability in the grades. It's the variability in the Y's. The sum of the squared residuals, the last column, measures how much variability remains unaccounted for after using the number of absences to predict the grades. In other words, our whole model that we're using is the fact that grades should predict, that absences should predict grades. That's our model. Absences should predict grades. When we try to do that, we still have some variation. The sum of the squared residuals is a measure of how much variation is still around after using our model in ways that we're not going to get into, except for one thing. What is the SSR divided by the TSS?
As a percent.
As a percent. So let's do it. The SSR was how much again?
971.36.
And the TSS is how much?
2,720.
Okay, when we do that, in our example, we get approximately 36%. So
and the example is still the absences versus.
Yeah, same example. So
Okay.
does that seem reasonable that we should get 36%?
Are you saying that the 36% now is the rest of the variables that are not accounted for?
Yeah.
But in the problem in the slide 6, we have 64% are for the variables not accounted for.
Oh, and they add up to 100%.
Oh my God. What? That's exactly it. This is how much is unaccounted for.
Okay.
R squared is how much is accounted for. So the R squared value. So now find, it says now,
So is that just a way you can tell if you're wrong? Like if you did the math wrong somehow?
well,
that it add up to 100%?
I mean, technically what happens is that you kind of just do one and assume this
The
is
other
more,
one is the other number.
this is more like from a theoretical standpoint more than anything else.
Okay.
You wouldn't actually do two. I mean, but it's never a bad idea to do things multiple ways to check. That's
Got
never
it.
a bad thing. Okay. So since we know that 36% is the proportion that is not accounted for, then how much does it account for? Well, it's the other 64%. So, right, that's the 64% that we got from the R value. Now, we saw that when we squared negative 0.8, we got 64%. Why negative? Where did that come from?
That came from finding R, didn't it?
Right, but what gave away that R was going to be negative?
That it was grades going down per absent.
Exactly. So the R squared doesn't care positive or negative because the negative sign goes away. R squared just tells you what percent of the variation is due to the model and what percent is not. In our example, 64% was due to the model and 36% was not. That was our example. Okay. Hopefully that's a little more clear than it was before. And it says here, you can see the difference in variability graphically. Notice that if we graph the grades, then you see that the grades are kind of spread out. Whereas if you graph the residuals, there's one little guy off to the left, but for the most part, they're very tightly packed.
Mm-hmm.
Okay, which accounts for the fact that the SSR was so small compared to the TSS. Right, the SSR, which was the sum of the squared residuals, was a much smaller value than the TSS, which is the total sum of squares, indicating that the percent explanation that is unaccounted for is going to be small relative to your model. That's the point of this whole exercise. So again, to sum up, without going into the details behind it, the SSR over the TSS represents the proportion of the variability in the Y values that remains after fitting the least squares line. Thus R squared, which is 1 minus that, is the proportion of the variability in the Y's that is explains by the relationship between Y and X. Okay, so SSR over TSS, that's what I'm not explaining. That's what I'm not accounting for. 1 minus that, which is your R squared value, that's what I am accounting for. Okay. Now, if all the points in the scatter plot had fallen exactly on the line, back to the same example. If every point on the scatter plot had fallen exactly on the line, what would, excuse me, what would be the R value?
1,
Well, you're going like this, right?
negative 1.
Negative 1, right? Perfect correlation is 1 or negative 1, but if it's downwards, it would be negative 1, correct? And what would the value of R squared be in that example?
Negative 1 squared, which is 1.
Which is positive 1. 100%. 100% of the variation. Okay. What would the dot plot of the residuals look like in that situation? Those remember what the residuals were in that little picture we just drew. The residuals were a measure of how spread out the unaccounted part is, correct?
Mm-hmm.
If there's no unaccounted part because it's 100% explains, then all of the residuals
Would be in the center.
would be, yeah, exactly. You'd have all the dots right at 0. All of them would have no residual whatsoever. Yes, no, maybe so?
Yeah.
Mhm.
And what would the value of RSS be? The sum of the squared residuals would be how much? If I take all those,
0.
0. If I take all those residuals, which are all 0, and I square them all, and they're still 0, and I add them all together, it's still going to be 0. Would the value of TSS be the same as RSS? Would the value of TSS be the same as RSS? What do you guys think?
The total sum of the squares. So since all the squares are 0, 0 plus 0 plus 0 plus 0, all of that, it's going to be 0. Would it be the same as RSS, which is also 0? So yeah.
Oh, wait. RSS is 0.
So TSS is the total sum of squares.
Correct.
But if everything's on the line, there's no deviations.
There's no residual. That's correct. Remember what let's see where we got the TSS from, right? The TSS came from adding these guys, right?
Mm-hmm.
Which was y minus y bars. Are all the y's the same? If we have a line like this or like this, it makes no difference. If we have a line like this or like this, are all the y values the same?
No.
So the y minus y bars are not all going to be 0.
Right. Okay.
Okay, which means it's not going to be the same. TSS is going to be bigger,
Okay.
all right?
Yeah.
It's not going to be 0 because this takes into account the fact that we have different y values.
Can you explain the residuals again and why
The
I'm really
residuals,
confused that we're talking about a
Yeah.
line that's up, but then we have a line that has all plots on 0.
yeah. So the residuals themselves are how far each y value is from what the line tells you it should be. So if I have a line like this, and I have a dot here, then for that x value, right? So here's my x-axis, here's my y-axis. For that x value, the line predicts that I should get this. This is my y hat. It's the predicted by the line. This is the actual y. The residual is this difference. It's how far off it is from the line. So if every point falls on the line, the residual is going to be 0 because the point is where it's supposed to be, right? Tomas, right?
Yes.
Okay. But if I have points all over the place, whether they're on the line or not on the line, the average of the y's is not going to be the same as each individual y. Even if they were all on the line, it wouldn't be that way. If I have a line like this, all these y values, even if all my points are on the line, my y values are all different. Correct?
Right. But is this saying that all the points are on the line since the residual is 0?
If the RSS is 0, then all the residuals are 0 and they would all fall exactly on the line. But the TSS wouldn't be 0.
No, because they all have different y
They have
values.
different y values. All right, so it would not be the same. And what would my R squared be? Well, R squared would be equal to 1, first of all, if they're all on the line. And it says that 100% of the variation in the y values is due completely and utterly to my my model of the relationship between the x values and the y values. Sorry. Again, things are not always clear the first time through, which is why you go over your notes, you do your homework, hopefully watch the videos. It's very hard to get new material the first run through. You try to get an inkling, an understanding, a basic idea. I kind of get it enough that when you see it the second time, it's like, oh, now I see what he meant here and there. So the term regression.
Can you interpret the value of R squared, please?
Yeah, so R squared is 1 in this case, right?
Okay.
Because all the data falls on the line. So R squared is 1. It means
Okay.
it means all of the reason why we have different y values is due to different x values, and there's nothing unaccounted for. I left nothing out that I needed to worry about. Absences was a complete and total predictor of grades with nothing else playing a factor in any way. Of course, we know that's not really true, right? There are other factors, which is why it didn't fall in a line. But if it ever did, that's the explanation. I have a total and complete understanding of why this is the case.
Thanks.
Okay. So the term regression was coined by Sir Francis Galton in the late 1800s. He was the first person to investigate human heredity, that's the right word, heredity statistically. Here's a 21st century version of some of the data he collected, okay? You have father's heights and son's heights. The average father height was 69.4 inches, which is 5'9.5" or so, with a standard deviation of 3 inches. And the adult son's heights was also the same average and same standard deviation, with an R value of 0.5. an R value of 0.5. Now, that's a positive correlation, which is reasonable, correct? I mean, tall parents usually have tall children. That's just genetics, right? Of course, now we know it's genetics, but this is back in the 1800s. Then this was like this was like, wow, hey, I just realized something. It's like, oh my God, gravity, you know, things that we take for granted. Back then, they were first discovering.
A novel idea.
A novel idea, yes. So here is the scatter plot, which certainly has a positive linear correlation, not very strong, positive correlinear. And we have the regression line, 0.5x plus 34.7 is equal to y hat. So let's see if we can graph that. So I don't know, something like 30, I don't know, something like maybe this, give or take. Not the worst guess, right? Is it right? Who knows? Well, it's definitely wrong because it's impossible to be perfect, but it's somewhere in the right ballpark. Would you all agree with that?
Yeah.
Okay. So here's a regression line. Here's my predictor. Right here, this formula right there. If you give me an X value, which is a father's height, and I plug it into this formula, out comes my predictor for the son's height. Is it going to be 100% accurate? Do you think father's heights alone will predict son's heights, or is there probably going to be more to it?
There's more to it.
There's more to it, which is why our R value is only 0.5. In fact, if R is 0.5, what's R squared?
0.25.
0.25, which means father's heights as a predictor only explains 25% of the variability in son's heights.
Wow.
What is the other 75% coming from?
Environmental factors.
Well, there's mother's heights. Let's not forget that.
All right.
Nature versus nurture. You know, you don't have vitamins, you don't feed them right, things of that nature.
No, literally, I mean, like, I'm not going to go too much into it, but environmental science, GMOs are going to be our downfall.
I don't know what you're talking about. GMO is not a real word. You just made that up. So there are things that I don't understand that are way beyond that you guys do, which is wonderful. I know things you don't. You guys know things I don't. That's the way the world works. Hopefully you're learning some of what I'm here to impart to you. That's the way teaching works. But whenever you guys teach me something new, I always appreciate that as well, because I like learning.
I mean, like, it's just like you can kind of,
much so.
I don't know if you see this within your high school students, but like they tend to get smaller and smaller with every passing grade. It's like a weird thing. Like we look at, I don't know, my AP environmental science teacher used to say this and everything. It's like you kind of see that they're getting smaller and smaller, and you wonder if it's the GMOs that they're eating that are affecting their body and their growth.
So you're saying the world population is just getting shorter?
A little bit, yeah.
Oh, that makes me feel better.
Isn't there like those random like bursts? There's like those random bursts of one grade being super tall again after
Right? Yeah, there's it. That's exactly what she said
Well,
too.
remember, as a statistician, you know that even if you have a linear trend or a trend in some way, there's always going to be variation.
Something can throw it off.
You're always going to have those anomalies. Excellent. Okay. So if you are a male, and I have a few in the class, you can use this equation to predict the height of any sons that you might have. If you are a female, you can use this equation to predict the height of any daughters that you might have. Okay. So I myself am like 5'8" something. So that's 68 inches. So 0.5 times 68 is 34. So my kids will be 68.7 if I'm 68. So they're actually going to be, according to this model, slightly taller than I am. Slightly taller than I am currently. Is that true? Who knows? I don't know. But that's what the model predicts. Okay. And similarly for females. Now, write an interpretation of R squared. Well, I just said it, right? R squared was 0.25. So 25% of the predictive power of this model is essentially accurate. That a father's heights will predict son's heights up to a variability of 25%. In the sense that I didn't really say that correctly. Let me rephrase that. variability in sons' heights is 25% due to variability in fathers' heights and 75% due to other factors. What are some of the other factors? Well, Megan just said something like gnomes or trolls or something. I don't know what that word was, but
Yeah, garden gnomes will be the downfall.
garden gnomes will be the downfall, exactly. Yes, so that's essentially it. Yeah, there are other reasons why, right? There are other reasons why, okay? Whatever they may be, okay? Now, finally, after all that's said and done, finally, we have a formula for the regression line.
Tell me to get up.
What was that? What was that? Oh, someone's on the phone. So finally, after all is said and done, we have a formula for the regression line. Y hat equals Y bar plus R SY over SX times X minus X bar. Now let's think about what all the things mean. Okay. Y bar is, of course, the average of the Ys. R is the correlation. SY is the standard deviation of the Y values. SX is the standard deviation of the X values. X bar is, of course, the average of the X's. And X is what? What does X represent?
A point.
8 points. In other words, every X value that you give me is going to have a different predicted Y value. You plug in the X value, plug in all those other numbers, and I will pop the Y value. Okay, that's exactly it. Okay. Are they deriving this line? No. They're just straight up giving it to you. Much like they gave you the formula for the correlation and a bunch of other stuff. They're just giving you this line. So their question?
Do you need to use 2 X points to be able to draw the line if you're going to use that equation? Only 2?
Well, I mean, in general, to draw a line, you need either 2 points or the y-intercept and the slope, both of which you have, right? You have options.
Okay.
You can plug in 2 points, or you can use the slope in the y-intercept. Either way works. Okay. So let's do an example. This scatter plot here shows the scores of a group of students on 2 tests. The test 1 mean was how much? According to this?
73.6.
73.6. The Y mean was how much? Or the test 2 mean was how much?
70.5.
70.5. What was the standard deviation for test 1?
18.1.
18.1. What's standard deviation for test 2?
19.5.
19.5. They give us all this information. And the R value is how much?
0.75.
0.75. Now, what is 0.75 squared?
I'm not doing it.
I'll do it. Hold up.
Common Core messed up my head.
0.75. 0.5625.
0.5625. Can you explain to me what that 0.5625 means?
It's the, oh God, I'm so bad at wording things.
You're so bad at wording.
Percentage of the 2 tests.
Is it, so that means that 56.25% of the data variability can be attributed to the test 1 scores.
Awesome.
So much.
Say that again, please. Say that again, please.
56.25% of the variability in test scores can be attributed to test 1
Go ahead.
score. You stopped sharing.
Yeah, I know. Just go ahead. Say it again.
Okay, so 56.25% of the variability in the data can be attributed directly to this test 1 scores, which is the X.
How do I?
Are you trying to spotlight me?
No, yeah, I was, but it wasn't. So I'm sorry. Right. So 56, I was trying to, but I couldn't figure it out. So 56.25% of the variability in the test 2 scores is attributed to the test 1 scores, which seems reasonable. That should be a large amount, like 50-something%. What are some other factors that we might have left out besides just test 1 scores?
Studying, sleep. food.
Studying, sleep. Maybe you woke up that day, you had a bad breakfast. Who knows what happened the day before, right? There's things that you can't account for, right? But a significant portion is due to test 1 scores. Very good. Okay.
Professor,
Yes.
what was that explanation again? 56.25% of the
56.25% of the variability in the test 2 scores can be attributed to the variability in the test 1 scores. The fact that the test 1 scores are different lends itself to the fact that the test 2 scores are going to be different. How much of that is the reason why? So they're claiming that 56% of the reason why the test 2 scores are different is due to the fact that the test 1 scores are all different. And the other 40-something% is coming from environmental factors. No, coming from garden gnomes, whatever it is. Okay. I don't want to, this is going to take too long and we're already at 8:11. So we're going to cut it here. I'm going to stop sharing. It jives. It jives. I'm glad it jives. We will continue this next time. It's an important chapter. It kind of wraps up correlation and regression and puts it all together. And I want to make sure everyone understands it. So I don't want to go ahead without really going over it thoroughly. But we'll do that on Wednesday. Okay? So have a great everything, everyone. And I will see you all on Wednesday.
Thank you.
Okay? I'm going to go to sleep now. So have a good night.
Professor, can you post the homework solutions, please, for regression
For last chapter or for this chapter?
for last chapter?
Okay, I can do that.
Thank you.
You're welcome. All right, everyone. Have a good night. See you guys soon.
Thank you.
Stay safe and healthy and all that kind of stuff. Okay. All right. I'm going to stop recording.